All right, back again. Happy holidays to everyone that celebrated. Good to see the start of 2024. As usual, we got Aaron, Steven. Any words of wisdom you want to share before we get started?
Happy holidays, everybody. Great to be back.
Yeah, happy holidays. So how it all
Uh,
go?
cool. Yeah, so we've been working on what is the probably one of the bigger releases we've had in recent
Ever.
days, probably ever.
Years. Years.
In terms of number of PRs and like amount of code that's in this, I wouldn't say like it was intentional to do that, but here we are. And so, Kyle, could you share my screen, please? Thank you. We're doing some final validation testing on this release, but hope it to be out in the next hopefully by the end of the week. We've been trying to get it out for some time now, and this includes a number of different like optimizations and bug fixes that will be great for just reliability before we move into the de-upgrade phase, which we're calling Durango. For the first part of this call, we wanted to just cover some of the bigger optimizations that have been added to this based on just network telemetry we've been following. And then after that, we'll go into some other research we're doing and talk a little bit more about the things that we're considering for a Durango Fuji release, which we can use to inform whether or not the community should vote for their ratification or adopt code for actual like a mainnet release. So yeah, first we'll go to the peer list ACK replacement. So Steven, go
Yeah,
ahead.
so this could go this whole conversation could take up the whole time here. But so the way that the way that Avalanche works and all blockchains work is it's generally built on top of a P2P network, right? So the P2P network or the peer-to-peer network is how validators and non-validators communicate with each other over the internet, right? So one of the most critical things here is actually forming those connections. And the way that Avalanche forms connections is that a node essentially connects into some nodes in the network. There are some like hard coded bootstrap nodes inside of Avalanche Go that can facilitate this for kind of first comers into the network, but you can also manually specify this if you don't want to use those. You can use anything that you specify manually. But once you connect with those nodes, they will respond to you as part of the handshake validator IPs. So essentially, people that they think that you should connect to. And those IPs are actually the claimed public IPs signed by that peer at their startup time, or actually whenever the last time their IP changed. So these signed IPs, anyone can receive them and then validate, okay, this is the person that claimed that IP, and then I'm actually interested to connect to them, so I will connect to them. In addition to that peer list sent in the handshake, peer lists were previously also just kind of gossiped throughout the network to guarantee that eventually all of the nodes would hear about all of the nodes that they wanted to connect to. Now, that was how things originally worked, and that was just kind of it. Around a year ago, we looked into like where our bandwidth was being used, and to a bit of our surprise, I guess not really our surprise because we already kind of had metrics on this, but like a shocking amount of bandwidth was being used just for these peer lists to essentially guarantee that nodes were connecting in with each other. So we decided to add a mechanism, which was the peer list ACK message, to essentially notify you on like when you shouldn't get resent IPs. So essentially, we were tracking which IPs we had sent to people and not sending any duplicates anymore. The idea there being, okay, well, we don't need to send a duplicate because we've already sent it to them. They already know about that IP. It's useless. So now all of a sudden, rather than using all this useless bandwidth, we only send bytes that they might need And then eventually over time, we'll be sending nothing because we've already kind of communicated all the IPs that we know about. So we did that, and on Fuji, that works actually pretty well. But as the number of nodes in the network grows more and more, so on the primary network now we have like 1,600 validators and I think 3,000 total peers. That mechanism still wasn't particularly efficient because it wasn't or it wasn't taking advantage of the fact that people get IPs from multiple people, not just yourself, right? So this change is to kind of turn that on its head, and so instead of proactively sending IPs, nodes will maintain a Bloom filter of the IPs that they know about and request any as a get peerless message. We'll send that Bloom filter to someone and say, hey, if you have any IPs that I don't know about that you think that I should connect to, tell me about those now. So instead of basically a push-based mechanism, this is a pull-based mechanism, which is similar to the kind of improvements that we've been making on the TX pool side with the C chain and P chain and X chain. So that was kind of the major point of this PR. So now we're taking advantage of the gossip that other people sent. So we're expecting this to have at least like a 10x bandwidth reduction of the bytes used for peerless gossiping. So which is a actually very like non-trivial percentage of the total bandwidth used by the node. So we're really excited to get this in. But as part of that, we were digging into a lot of just kind of like how our Bloom filter worked. So there are a couple kind of prereqs to this PR to make sure that all of our Bloom filter logic was set up in a way that we were really confident with this data usage. So one of the things that we had to think about was guaranteeing that someone couldn't grief another validator. So as soon as you introduce these peer lists, right, you have to once you introduce the Bloom filter over IPs, Bloom filters are generally not kind of like Byzantine fault tolerant because you're essentially hashing something into a very small set of numbers. So if your Bloom filter is say like I don't know, like 16 kilobytes or something, what you're actually putting that into is like a 14-bit hash, if you think about it. And a 14-bit hash is certainly not, a cryptographic hash at the end of the day. So a lot of the work that goes into making sure that the P2P network is resilient against these things because people don't generally update their IPs. These IPs are fairly static. We introduce essentially some various hashing on a per Bloom filter basis to essentially rotate the value, like the entries that are getting placed into these on a per node basis. So if someone's trying to attack the system, they want to basically have collisions into this 14-bit hash, which is very easy to do if you're grinding. But if you don't know what you're actually grinding against, then it's very hard to actually like attack that system. So a lot of the work in this PR has kind of been like making sure that like we're guaranteeing over time the nodes will eventually connect, even in the case of malicious parties trying to prevent some nodes to be gossiped around. I know, Patrick, you pulled up another PR, which was the optimizations for the Bloom filter stuff. So we also dug pretty deep into optimizing that. I have one more PR that I'm working on the write-up right now because I went a little bit too deep or deeper than I probably really needed to. But there's some like subtle hints that you can give the compiler to move the some panic checks around, some division by zero checks outside of the hot loop of the Bloom filter checks. But I was really happy with kind of this PR to optimize both Marshall and parse.
What he's
So
telling
especially
you is that basically a 99% reduction in the runtime isn't good enough, and that he wants to also reduce it more with compilation.
well, so if you look, so the Marshall and parse here were really nice because we got like essentially like a few orders of magnitude improvement, but the contains check, it was only kind of a like a half nanosecond improvement. But I think that we can eke out another half nanosecond improvement on that that contains check. If anyone out there can figure out how to like get the array out of bounds check moved out of the loop as well, absolutely cap off to I was trying to figure out if Golang just had like, you know, a Rust equivalent of unchecked to like just explicitly just say like, yeah, give me undefined behavior. I don't think we would have actually merged this because it's really gross, but like I don't think that Golang has that capability either. But yeah, anyways, so I've been having a lot of fun optimizing the Bloom filter stuff for sure. Especially happy with what came out of parse. Just kind of like changing the way that the Bloom filter is represented was able to really optimize parse, which is super useful because now all of a sudden it's a lot cheaper to handle get peerless messages. Optimizing the Marshall side is nice, but generally you don't have to worry about that nearly as much because you're the one that actually like choosing to Marshall and send it. Whereas like the parse side, you're actually handling that message. So yeah, anyways, I don't know if you guys have anything that you wanted to talk about specifically with this, but I think that optimized Bloom filter is also being incorporated into the C chain, X chain, P chain, TX gossip as well. So
Yeah.
that should make our
Yeah,
CPUs a little happier.
I wanted to call out because I rarely make PRs into Avalanche Go anymore, and I did get one in related to this. So for folks at home, you'll find that one of the things when you use a Bloom filter that gets kind of annoying is that like actually determining the right size to represent the set of elements you have. And so I was playing around with some tests in some ADVM actually and found that in different circumstances, we would have like sets in this case of the mempool that would grow. And then because of like some pre-configured like expected size, we would just continuously like reset the Bloom filter, which, you know, causes like this O of N iteration typically over the elements. And so I added this capability to automatically grow the Bloom filter size based on the target number of elements that you want to represent. Really not the target of elements, but the target of element churn you want to represent, like elements that are added, not like the size of it, which you would typically change based on the size of the set that you're using to like interact with the Bloom filter. So this is another fun one. So you may wonder, like, why you guys spend all this time on Bloom filters? Like, what's going on? So earlier on in the network, and this is something we just hadn't really changed since the beginning, was we used a lot of push gossip to synchronize information across nodes. But you know, through our own, you know, telemetry as well as like also this is not super novel, right? Is you can dramatically reduce the amount of useless bandwidth you utilize by polling or pulling gossip rather than pushing gossip. And in many cases, it can actually even be faster. So for a lot of this stuff, it ends up being like a win-win where like you get what you're trying to do done more quickly and you use dramatically less bandwidth and CPU in the process. But in pull gossip to like communicate what you actually want in these sort of systems, doing it efficiently, turns out Bloom filters are like one of the best data structures to use to actually communicate like what you need from someone about what you don't have. So for example, like a while ago, we added the ability to request transactions from people based on sending them some Bloom filter of what we already have in our mempool. They say, okay, I'm going to iterate over my transactions. Oh, doesn't have this, doesn't have this, doesn't have this. You probably want that. I'll send it to you. And so we now use Bloom filters pretty pervasively through the like networking logic, similar to how we use like BLS all over the place or will soon. And so making sure this was well optimized and easy to utilize was a really important thing to do. So also want to just clarify that.
I think there was one question in the chat asking if the Purelist update will be pushed to the C chain. So The P2P network is kind of a shared resource that's used by all of the chains in the network. So optimizing this improves the kind of validator and non-validator performance of all nodes running Avalanche Go. So that's all of the nodes that are kind of like hosting or running the C chain. So I guess a short answer to that would be
the other thing that this also helps prepare for is ACP 13, which I know we've talked about a good bit in the past around like how you can have subnet only validators. Well, in that world, like we would expect the number of peers that actually connect to the primary network to grow quite a bit. And if the peer synchronization protocol and like all these different protocols to like gossip blocks and gossip like how to connect to other people are not efficient, we're going to have issues. And so this optimization is like an important step in preparing for that future as well. So may update the ACP to indicate that this is like work related to that, but that's really how you should think about it. It's like, yeah, we want to save bandwidth for nodes like in steady state, but we also want to prepare for this world where like there's dramatically more nodes and that like there's a really efficient peer synchronization protocol. Yeah. So yeah, that is that. Aaron, anything you want to add on top of any of this peer stuff?
No, nothing on the Bloom filter side for the P2P layer.
Sounds good.
Also, if someone wants to make a PR suggesting to use cuckoo filters instead.
I actually was gonna bring that up. I have the tab open on cuckoo filters, but I decided not to make the joke.
Yeah, I don't know that such a PR would get merged, but I would be fascinated to look into it. So I think I have personally looked into like cuckoo filters a number of times, and I have definitely like never really understood like the failure case of cuckoo filters. So cuckoo filters are supposed to support like removal from a Bloom filter, which would be really nice because one of the major reasons why we have to reset a Bloom filter is, as Patrick said, this churn. So like as you add more and more things to the Bloom filter, there isn't necessarily a way to remove something. So the way that we remove it is we periodically just create a new filter and re-add the stuff that we still care about in and say, okay, that's like, how it works. But if you could like, remove those things kind of on the fly, then you wouldn't necessarily have to reset it unless just the size of entries is growing too much. There are some things like counting filters and things like that that are very kind of straightforward. But a cuckoo filter is essentially relying on like hashing and like I forget what it's like. Anyways, but yeah. So would be interested if anyone was particularly passionate about these kinds of design decisions. But
yeah, the next topic we're going to go into is around ACP support. So a number of people had mentioned that like the existing mechanism for like signaling support inside of ACPs is suboptimal. So for those at pay attention, this is what we call the ACP straw poll. And so I'm going to have that link shared. But the idea was on every open ACP that is considered implementable, anyone could sign a standard message, like saying like they're in support or not in support of a protocol with additional, like of an ACP with additional support. What this meant, however, was that anyone that had a validator like would have to dox themselves by like or like connected to a GitHub account to put up such a thing, as well as this is just cumbersome. So like putting this all inside of like the core app and then like signing it and everything is just like there's got to be a better way. So we had some conversations internally about like suggestions we could make to the foundation around like better ways to do this, and Steven and I came up with an idea, and then Steven ended up really pushing it forward. Is this thing called ACP signaling. So the idea is, and I'll let Steven talk about the specifics or like some edge cases we could think about, is that for when you're interested in signaling support for or against an ACP, you can specify a flag basically on your node that says ACP support or ACP object. And that is provided either on the command line or in a config. And then the really cool thing is that all nodes listen for people's preferences, and this is part of the handshake. And so when you express your preferences, every node keeps track of like the stake weight and number of node IDs that are voting for or against something, and then explains it or like makes it accessible in an API. So now anyone will be able to say like what the stake weight is that is in support or against particular things, so that when people are considering whether or not an ACP should be adopted, they understand like what the balance of people supporting or against it is, and if it was adopted or put in the code with some sort of activation date, like what's the likelihood that it would fail and the network would fork or stop because of that. So we're super excited about this, and we'll see if the foundation chooses to adopt this as like the recommended mechanism for actually signaling support. But in the least, it should be possible to create some pretty cool APIs and dashboards with this information.
Yeah. One thing to just re-stress is this does not actually activate any ACPs. This is just a mechanism of signaling opinions. The reason that this doesn't activate ACPs is because one, the threshold for communicating these is implementable, not implemented. So like it doesn't necessarily mean that like either Avalanche Go now, or if we have other clients in the future, it doesn't necessarily by voting on this mean that that client has actually like implemented it and it could be activated. But also there's some really interesting edge cases around like just very like decision thresholds and things like that. So what you really need to do if you wanted to have this activation happen is you actually have to encode it kind of inside of a consensus protocol somehow, whereas this is right now just strictly over the PDP network. So it doesn't necessarily rule out eventually having a kind of more automated mechanism of essentially governance of like making modifications to the chain. But this is not that, just to be clear.
Yeah, I think Bitcoin has a rule where like you signal like your preference for different things in the blocks that are built as a miner, and then over so much time, is it 2 weeks or something like that? If like 90 or 95% of blocks support activation of something, then it becomes like a new opt-in rule or like a soft fork, I think they call it. So you could definitely do something similar here at some point and like really automate the activation of different features rather than strictly like requiring like a manual activation after fact.
Okay. I see a question in the chat. Do you guys take questions from the chat? Sometimes, yeah.
So as we're talking about ACP stuff, like, having some estimation of support for or against different ACPs is obviously really important, as I mentioned. There's a number of ACPs that are currently up for discussion that are either implementable or otherwise. And so a lot of these implementable ones, so I think we have keychain native transfers, activated Shanghai EIPs, virtual machine application errors, warp messaging integration, that's probably the big one. Subnet ownership transfer and removal of pending stakers have actually all been implemented inside of Avalanche Go. And so I think there's corresponding links to all of them in these ACPs as well. And a big part of actually like preparing for or against on these things on the network is whether or not they're stable and useful. And so this is what Fuji is for, is testing these things in combination to make sure that they are stable, particularly big changes like the teleporter changes that are coming and warp messaging support on the C chain. And so we're planning to spin up what we're calling the Durango release, which will actually implement or activate everything that's currently in this implementable row on Fuji in preparation for potential activation on mainnet if folks are supporting it. And so this will allow us to test everything and make sure it's all working before anyone, seriously considers the activation of them on mainnet. So that release, could come in the next few weeks, hopefully, depending on how V1.10.18 rollout goes. But if you have concerns or questions or anything about the implementation of those, like now would be a good time to definitely reach out in the discussions. But the other thing is that once ACP signaling support is added to V1.10.18, or like once that release is out, like it'd be a really good idea if you feel strongly for or against any of these ACPs to update your node so that you can signal your preference for them, whether for or against. So I wanted to give an update there because a lot of people have been asking like when's Warp going to be accessible on the primary network, some stuff like that. On the other ACPs, like still interesting stuff. I think there's still a lot of kinks to work out, particularly on the ACP 13. But I think things are moving in the right direction with a lot of these other changes here. I think that's one of our primary focuses right now is just getting to the point where we can test out all of these ACPs that are currently considered implementable, so people can vote or try to consider them for activation on mainnet. Signal their support, not really vote. I'm not sure if there's anything. We've talked about all these at length, so I don't think it really makes sense to go into each one again. If you want to hear more about them, like you can watch some of the previous dev community calls where we, talk about each one at length. I'm not sure, Aaron or Steven, if there's any like particular updates on any of these that you wanted to call out that we figured out during the implementation that would be useful.
No, I think each of them should speak for themselves if anybody wants to take a look before updating their node and deciding which ones to signal for or against. Each of them should be relatively self-documenting. We've talked about them, each of them at length before. I don't know. What do you think, Steven?
Yeah, I mean, I'm just itching to get the 1.11.0-Fuji out and start playing around with it. We definitely hoped that it would that we'd kind of already have gotten to that point by now, but just various things with the holidays and trying to wrap up those last couple kind of optimizations of the P2P network have kind of pushed things. So
the biggest motivation for us is just so we can shut off all these old like networking mechanisms and like really take advantage of like all the great new stuff. So like outside of the features, that's a big
this is something that a lot of people don't maybe know about or kind of understand. Like, so in Avalanche, Avalanche Go supports all versions running the current minor version. So running 1.10.0 through 1.10.17, any of those nodes can sync the network. If you're running 1.9.5 or something, that won't be able to connect because it's not running the kind of like correct version. So whenever we do a new kind of upgrade, we can remove a ton of code supporting kind of like historical versions. So there's a issue in Avalanche Go that's just tracking all of the to-do remove code things once we activate 1.11. So there will be a number of significant bandwidth improvements once we remove that, because we've changed a lot of the gossip stuff from pushing to kind of a push-pull mix. And by doing that, you can really reduce the amount of pushing that's done because you can rely on pulling to have a much faster convergence rate. So I will also throw out so there was a question, what is the process of joining the a Vox team? So I would say that's an interesting question. So I would say to kind of join like the developers on Avalanche, at the end of the day, like if you want to develop on Avalanche, we are so excited to have just random PRs, random kind of contributions in. Like by no means does is like being a developer like required, you don't have to be an Avalabs employee to be an Avalanche developer, right? I've seen a number of like kind of PRs and upticks, some people in the Hyper SDK that have started contributing there. That's really exciting. seen some stuff in Avalanche Go. So I'm really excited with like kind of that growth, and I think that as we've kind of been pushing for these kind of dev community calls, like I'm hoping to kind of get more of that kind of participation and conversation within like the developer community. So that's a big reason why we kind of do these. But then Ava Labs is also always hiring, so that's more of a Patrick area though. I'm not a manager. I avoid management like the plague.
Yeah, we have
So
4 open headcount on the platform team, so like protocol engineering, and you can check out on Avalabs careers. So this is a very small digression into what our topics of conversation were today. But yeah, if you're interested, like there's places to apply. We're looking for folks to join us and help continue to grow the team on a number of different areas, but particularly within consensus engineering and virtual machine engineering. So
Yeah,
cool.
I was gonna say, maybe another thing we could do at some point during these calls is just go through a couple of issues if people are, especially if people on this call are interested to just actively contribute open source. We could definitely take a little bit of time during these calls to just go through a couple of good first issues that people might want to dive into. Could even have people up at some point. If anybody's interested, just say so in the comments.
Yeah, I think that's like more interactivity with these things is definitely something that we want to try and cultivate somehow. And so I've had some conversations with some folks around different ideas there, but especially around like Hyper SDK and like having like almost like open stand-up calls would be really fun. So much to consider there. But now we'll transition into some research that we've been doing on performance improvements to consensus. So Stephen, if you have your slide deck or something like that, you can kind of get ready here while I bring you in. But long story short, a lot of people have been asking, like what sort of work or research is being done into like how to improve the end-to-end finality of Snowman or Avalanche and its resilience, in different situations. And so we've been working on at least two, important research directions that are more on the theoretical side. And I think we should cover those now as like kind of a preview of like some of the things that we're thinking about. So once Stephen is ready, we can go into that. In the meantime, I see one quick question, which is like, how would you compare Firewood to Monad? Monad isn't open source yet, and I have no idea what they're doing. So as soon as they share more details on it, we would be happy to do a deep dive. One quick tidbit for people listening is Firewood is now has met the performance of the MerkleDB, so they're now equal, which is really exciting. They're very close to it. So now it's time to push it, beyond that, which was the original goal. But getting it to at least parity is a really exciting milestone, given it's an entirely new database written from scratch. So with state sync support and everything, so it's a big milestone. But yeah, once they publish more information, I think it'd be a great conversation to have, and we'll probably include some of the Firewood folks up here to debate it. Maybe even include the Monad folks. It'd be kind of fun. All right, Stephen, go ahead.
So I'm not gonna run through this whole presentation. So recently got back from an IC3 event, and so this was a talk that I gave there. But to just kind of go into this, the Avalanche kind of protocol has like a number of kind of sub components for consensus. So there's like the Slush, Snowflake, Snowball, Snowman. Snowball and Snowman build on top of Slush and Snowflake, and this kind of talk, like this presentation was really focused on just the Slush and Snowflake case. So we generally think of, we have some nodes in the network, and they have some kind of preferences in the blockchain world. This is essentially, a block that you can choose to either like accept or reject. So in this case, if it's two colors, red and blue, you would have kind of two different blocks at the same height. You can pick one of them. So the way that Slush works is this is kind of the core subsampling process, and you're essentially just taking whatever the network majority is, and you're trying to adopt that color And so we go through, and in this case, we started to just kind of randomly pick blue from a 50-50 split, and then the network quickly converges. So Snowflake builds on top of Slush by actually telling you when something is finalized. So in this case, we have a red node to kind of denote like a Byzantine adversary, or a node that's just kind of always voting against the crowd. But in this case, with Snowflake, once you see some number of consecutive polls reaching your kind of required threshold, then you'll end up finalizing. So in this case, this node samples goes from 4 consecutive to 5, and it ends up accepting blue. So you can see here we have this kind of like over time convergence to blue over the network, which is really nice. So this kind of touches on, there's a point where the network is going to essentially guaranteed to tip that way. So rapidly you'll go from, once you're past the tipping point, the network will rapidly converge to blue. And in fact, you're essentially guaranteed that the network is going to go to blue. And then there is essentially the finalization point where, depending on your safety threshold, you are determining that the network is sufficiently blue that you are willing to kind of commit. So any kind of finalization detection mechanism that you have, once you are past the finalization point, you can detect that the network is past the finalization point, then you can commit. So if we remember a few talks ago, we had the dual alpha PR. So the dual alpha PR separates out the alphas into two different ones. One is for the majority finding portion of the protocol, and the other is for the finalization case. And the reason for that is because if you don't do that, you have to have an alpha sufficiently high to have high enough safety, but that can cause your preference selection to take a really long time if you're in a kind of 50-50 split with a high Byzantine resilience. So if your alpha is too high, then you can end up kind of looking like this without the dual alpha approach. With the dual alpha approach, we end up introducing two different alphas, and then the convergence can kind of proceed independently to the finalization detection. So so that's kind of something that we've already merged in. We haven't actually activated this yet because we're still running through the actual like probabilistic analysis and work to kind of make sure that the numbers are in a place that we're happy with. And then we'll put that out and kind of probably write up an ACP to actually activate this. But another kind of interesting area is further reducing the number of round trips that are required. So previously we were talking where beta is essentially a constant value. But what you can actually do is, depending on the results of the network, your alpha confidence can actually be a curve, which is a curve depending on the beta. So like beta is the number of like consecutive polls that is needed to return. And then alpha, rather than being a static value, can actually be interpreted as the actual value that you received in the network. So if we look back here, the number of rounds to commit here is always going to be at least beta, because we kind of fix that as our security parameter. But here, if you had a higher alpha, you can tolerate a lower beta and still have the same safety kind of curve. And so by doing that, we can actually reduce the number of rounds to commits potentially significantly, especially in the kind of normal case where you don't have a Byzantine adversary. You can drastically reduce the rounds to commitment. So that's kind of some research that we've been working on recently. It should be able to kind of reduce the number of rounds potentially as much as, I think this slide shows that it might be able to reduce it as much as like a factor of like 6 or 7. So yeah, currently really interested in that to kind of get the time to finality down even lower. So I think right now the time to finality is around like 1 to 2 seconds. So hoping that we can kind of reduce the time it takes between polling, which I think is like 1.2 of those seconds or so. So if you take 1.2 divide by like 5 or 6, like you're starting to get down to like that kind of magical like 300 millisecond, 250 millisecond range that we're really excited by, because at that point you're starting to get to more theoretical limits on like speed of light and things like that. So this is kind of some of the research that we've been doing. This hasn't been encoded into Avalanche Go yet at all, just because it's a little bit more complicated than the dual alpha to implement. But yeah, this is definitely something that I'm really interested in working on. I think that's about it here. Stop sharing that, but I don't know if Patrick or Aaron had any comments.
Yeah, I mean, I think the intuition, right, just as to wrap it up a bit, is, hey, like normally we're getting beta consecutive polls of some sort of alpha over k, and if it's above that alpha, we consider it successful. So it's pretty, like we treat 19 out of 20 consecutive polls the same as we treat 15 out of 20 consecutive polls. So like if we get like 4 or 5 like consecutive polls of just like 20 over 20, that gives us the same confidence that like the network is colored very deeply in one direction, and thus we should be able to stop polling much sooner. But right now the engine doesn't take that into account at all. The other thing to keep in mind as well is like if the samples are larger, so like instead of groups of 20, but instead of groups like 80, you can have many less round trip times, and maybe even get higher confidence if you have like, let's say 80 over 80 tells us a lot more than 20 over 20. And so if we can use that information, we can even have less round trip times. So in like some ideal world, depending on how you set the error tolerance you're willing to accept on these polls for finality, you may be able to greatly reduce the number of round trip times you have to actually get consensus over some sort of block data.
Yeah, the latency that we see right now, as Steven mentioned, around 1 to 2 seconds, is really dominated by essentially beta, or the number of polls that we require to be successful in a row in order to accept something, divided by the number of polls that we perform concurrently. So we basically will take, if we have beta polls and we're performing 4 of them at a time, then that'll be 1 round trip time waiting for those responses to come back. And so we'll end up with roughly 5 round trip times if we do 4 polls, wait for the response, and then go to the next round and so on. I think right now we have concurrent polls set to 5 and beta set to 20. So we end up with about 2 seconds. Is that right, Steven, for the defaults? I think that's right. It's close if it's not right.
I thought beta was 30 and concurrent polls was 4, but I have to double check.
Yeah, but that ends up dominating our round, or the total latency to accept a block once it's been issued into consensus. But if we can reduce the beta that is required to accept, based off of, just like Stephen and Patrick said, taking advantage of the additional information that we get out of these polls, or the additional information of treating something as not just X is greater than or equal to alpha, but exactly what that value is, whether that be 15 out of 20 people set X or 20 out of 20 people set X, gives us a much stronger source of information. So we can commit earlier and still perform those polls concurrently in order to accept much more quickly. So hopefully we can reduce that consensus latency significantly.
The beta is 20. You were right about that, but the concurrent polls is 4.
Cool.
Yeah. So the other thing too, which is someone actually alluded to here, is like, can validator sign messages with their BLS keys during consensus? So there's a bunch of stuff in this direction that we're like looking into. Like one of the lower hanging things you could think of is, not to say that we would or should or shouldn't do it, is to say, all right, I've been doing this polling. I'm at the tip, like I'm a validator, and like I've now completed my polling for this particular like height, and I've locked in. I'm not going to revert my decision. I could gossip like a BLS signature of my locking in at that point. And then anyone that's actually like trailing the network who doesn't even want to maintain that many connections can just wait for like an aggregate BLS signature to be formed with like some percentage of stake weight and use that to actually finalize. So like some people have asked, like, and other networks have done this, which is, I think it's pretty cool. Like, but you can have this notion of like light clients on phones or like in the browser where you can like just listen for, acceptance over certain data. But where it gets really interesting is in this world of like partial sync on subnets. So when you want to recognize transfers on the C chain as like deposits into your subnet, if you're not running the C chain, you have to like somehow rely on some external source of truth to say that actually happened on chain. But if we have this notion of signing like periodically accepted headers, anyone that's not actually syncing the C chain can utilize those headers to verify information was actually valid when they fetch it from some source. And so this is a huge improvement, at least for that case, which is also part of this whole push for sub-node validators. And so having better like BLS usage, I think on the primary network is going to unlock like significant number of use cases. Yeah.
Yeah, big thing with that is that we probably wouldn't actually use the BLS signing during the consensus process, but as a kind of like follow-up consensus process to essentially allow like clients. One of the really kind of interesting things about Snow consensus is it actually doesn't use asymmetric keys in the actual like consensus polling. So it's a fully kind of symmetric encryption communication mechanism modulo the initial handshake. So you're essentially performing a Diffie-Hellman there with a like asymmetric key identity. But once the kind of connection exists, then the communication is extremely fast because you're just using that symmetric key for essentially tamper-proof communications. So that makes the kind of consensus cryptography very lightweight, which is really nice from a performance perspective there.
Yeah. So I think that's like another one of those big things that we're really trying to do that'll also help us optimize, more BLS usage will also help us optimize voting as like the number of participants also increases, as well as like just more voting happening on chain when there's more subnets, especially elastic subnets. So you can expect all that stuff to come out in different ACPs and such. I would expect, at least from us, over the next few months. So yeah. Go ahead.
I think there was one question about the finalization. Like, how do you recognize if there's like a low number of BF or like Byzantine faults in the network in order to like commit faster? So you don't actually have to know how many Byzantine faults there are for the fast commit path to work. The Byzantine the fault resilience comes from detecting that you're past the finalization point on the network, and some Byzantine faults can make it more difficult to detect that. But like, if you're able to detect that you're past it, then you can commit. So it's not necessarily reducing your fault tolerance by committing earlier, but it's just able to commit sooner in some cases. I don't know if that made sense.
So the Byzantine fault tolerance, or the amount of faults that you want to withstand, is an input to calculating this, right? Because that sort of goes into So essentially, the BF, or the portion of the network that you want to be resilient towards Byzantine faults, is an input that you want to specify. So if you say, well, I assume that the network is 90% honest, and I'm okay with making that assumption, then seeing some negative consequences if that is violated at some point, you could specify, okay, I want to resist up to 10% Byzantine faults, and then you'll potentially commit much more quickly and be able to observe that more quickly. So for example, for MEV style nodes that are trying to make money as quickly as possible, they might care about getting those finalization results very, very quickly on their nodes. So they might say, well, it's usually a good assumption that, in reality, it's usually a good assumption that less than 5% of the network is Byzantine at any one time. That's not necessarily to say that you actually want to perform any action based off of a block being accepted in that case, because the whole point of these types of systems is to withstand infrequent events where somebody might try and attack them, or any type of attack might occur. But for practical applications, you might want to say, well, actually, I would prefer to prioritize getting these results much more quickly, and I'll go with a lower Byzantine tolerance. And so one alternative application of this, I think Solana actually put something out that a lot of people were asking us about, which was, hey, they have this lower BFT resilience that allows them to have a faster commit path or a faster let us tell you when something is finalized. And so that was basically saying, well, assuming that less than 10% of the network is Byzantine, then we can tell you this information about when something is accepted more quickly. And so a lot of people were saying, well, hey, can you guys do something similar to that? And so this will actually do exactly that, which would be essentially if you want to have your own API node that will tell you this information as quickly as possible. If you wanted to operate based off of this assumption that a lower amount of the network is going to be Byzantine, then you could observe those results more quickly. So this will sort of open up, and practically speaking, what this might do for people that want to build applications is if you want to operate under the assumption that this is very, very rare, and for your application, it's okay to say, well, once in a while there might be some Byzantine fault, and at that point it'll be all over Twitter, and we might, detect it through some other means. But if that doesn't impact your application very directly, if you want to prioritize getting the lowest latency confirmations possible 99% of the time, then what you might do in that case is put in a Byzantine fault tolerance as an input of, let's say 10%. And then you'll actually see a lower latency to finality than everybody else in the network, which would be really cool.
Yeah, the hope here is that at the end of kind of all of this, Avalanche Go, rather than taking in like alpha, K, beta, will take in like the kind of percent of Byzantine faults that you want to tolerate and like the error probability of a failure. And then from there, it'll kind of derive the optimal kind of values from that. So that's kind of the end goal that I think would be really great, because then essentially if you're an API node, like Aaron said, then you can essentially just reduce your Byzantine tolerance and say, you know what, I don't think that more than 5% of the network is going to be Byzantine to me. And then you can set that and you'll end up committing faster and you'll have kind of a better UX for your nodes. So, or for your users. So
yeah, just to reiterate, this is very specific to what you're using that API node for. Yeah.
Also, I would not recommend changing any of these parameters on validators because that would be interesting.
Cool. Well, yeah, I think we're wrapping up here. So, thanks again for stopping by. There was one question someone asked, like, tell us more about fortifying decoupled state machine replication with bricks. Stay tuned. So,
bricks, is that a new name? Wow.
We better shut this off. All right. So,
how do you pronounce
thanks everybody. Thanks everybody. We'll talk to you guys later. All right. Bye.
See you guys.